So let's restart after the nice surprise talk on spherics. We go back to the history of the CMB with the second panel, lessons learned from WMAP and Planck. You see the speakers. Let me remark that this is a little bit less consigned to history because these missions are still alive. The data are available, widely used, and plan to remain for the community for a long time. So yes, history, but a lot of lessons learned. So let me invite Chuck Bennett to the podium to talk about the WMAP experiment. Use that. Actually, it's on the microphone. Yeah.
Okay. Can you hear me? Yes.
Yeah.
Okay, so my name is Chuck Bennett, and my assignment is to talk about lessons learned from the WMAP space mission. I'm going to start by giving a very brief, quick summary of some science highlights, and then move on to the lessons learned. I wanted to begin by emphasizing that the WMAP science team was small, certainly by today's standards. All of the investigators are listed here. At some time or another were on WMAP team. 26 people. The ones in yellow were the ones that were original signatories on the proposal. The timeline here, just to put WMAP in its history perspective, in 1995, we proposed to NASA. The proposal was accepted a year later, in 1996, and then we were off and running. 5 years later, in 2001, we launched. And then in 2003, we had our first science results. And then we operated for 9 years till 2010. And we had our final papers in 2012, submitted in 2012 and published in 2013. And that was before Planck results were published. So that means the WMAP papers were not influenced in any way by Planck. They were done before that. So let me talk a little about the run-up to WMAP. As we heard about this morning, early this afternoon, Kobe DMR discovered anisotropy in 1972. The beam size was 7 degrees, so all of these fluctuations were super horizon. And at least the CMB community, knew very widely what to do next, which is to go after the subhorizon fluctuations. And there were all kinds of meetings in different groups trying to think about this. To me, the big problem was that there was no launch opportunity. And so I schemed together with Steve Holt, who was the director of science at NASA, to try to convince NASA to do smaller, less expensive missions. And we had NASA managers in the room. We invited astrophysicists from around at least the United States to come in and say, what would they do if they had the opportunity for a smaller end mission? And there were lots of very interesting ideas. Some of the managers only wanted to manage huge missions, but we actually won in the end, and the NASA headquarters decided to introduce the so-called SMEX and MIDEX programs. And so they issued an announcement of opportunity, the first one for the MIDEXs in 1995, and 2 missions were selected. One of them, IMAGE, is a heliospheric mission, and MAP, as it was called then, was the astrophysics selection. MAP was named because we wanted to emphasize that our objective was to make a map of the sky. Later, I wrote a letter to NASA asking them to rename the satellite in honor of Dave Wilkinson, and that's how it became WMAP. So while everyone in the CMB community understood what we wanted to do, I talked to a lot of people in the broader community, senior people, that were very doubtful that you could use the CMB to measure things like the Hubble constant or other properties of nature. So there was a lot of disbelief, and this caused us to write into our proposal, based on red team, blue team reviews and things like that, what if you don't see any acoustic peaks? So we actually had a line in there that said that that would be even more revolutionary. The guiding principle for WMAP that I think we all shared on the team, I remember Dave Wilkinson saying once, I don't want to do everything, I just want to do something and to do it soon. And that was reinforced by the cost cap of the MIDEX proposals. It had to be technology ready, had to be $70 million cost cap, and that worked fine for us. The idea that the science team had was to concentrate on the largest angular scales that are still sub-horizon, and that was translated into the language of measuring the first acoustic peak to the cosmic variance limit. But we knew from our simulations that if we did that, that we would measure the second peak extremely well and do okay on the third peak. And in the end, in the final result, we were cosmic variance limited to a multipole moment of 457. And we had a signal to noise greater than 1 all the way out to almost 1,000. And so, as you all know, this is the first full sky sub-horizon scale CMB anisotropy map. It matched very well with the Kobe pattern that came earlier, but with, of course, higher resolution. And then a bunch of results flowed from that. I'm not going to spend a lot of time on these, but it was the first time we had a simultaneous fit to 6 cosmological parameters from the CMB. It was several items related to inflation, first detection of a TE large scale anti-correlation, first detection of NS less than 1, first precision sub-percent detection of flatness, and the first time ruling out inflation models based on the tensor to scalar ratio and the spectral index. And of course, all of these things have been done much better now by Planck and ACTR6 and things like that. There were results with the neutrinos and even early hints of the Hubble tension. When we took our WMAP data and combined it with the baryon acoustic oscillation data of that era, we saw that the data wanted a lower Hubble constant. When we combined instead with the distance ladder H0 measurements, it wanted a higher one. Now, at that time, this was not a statistically significant effect, but it has since become one, and this was the first signs of it, I think. So the top left, Chris Gorsi already mentioned Ned Wright. Ned Wright made the plot on the upper left, which I managed to unbury. And this was a snapshot. He fortunately labeled it. It was made the 3rd of December 1999. And this was a snapshot of where the community was then. One thing I wanted to note about this was that there were a lot of CMB teams at that time that were competing with each other. And you can see there's a lot of scatter in the measurements. The other reason I wanted to show this is because the model that Ned put through this was NS equal 1, H0 was 50, and there was just cold dark matter and 10% baryons with no cosmological constant. And so that was his shot at it back then. Just before we published our results, we took another shot at this in the bottom, in the bottom left here. Barely see that. So the idea there was just to take some of the best experiments, take a running mean through it, and raise the uncertainty gray level until it was statistically consistent with the data. And I thought that would represent the state of knowledge at the time. And then on the right is our final WMAP result, so it's quite clear that made a lot of progress doing what we imagined. Now, at the time, in our final results, we had SPT and ACT data, also shown here, which we called ECMB, extra CMB observation on the smaller scales. And many of our parameter fits, we showed what it was like with and without those data included. As I said, ACT, for example, had this data at this time, but the current ACT data has much, much smaller uncertainties here. And again, we have the Planck data now too. So I mentioned the large scale TE polarization. So the WMAP had polarization sensitivity. It was never required to have it. And there were times in the development where we could have solved some problem by getting rid of it, but we never let that happen. So while it was not optimized in any way for polarization, it was polarization sensitive, and we tried to make use of that. In terms of optical depth, before WMAP, there was no CMB determination of the optical depth value, only upper limits. And then our final WMAP determination is shown here again with that ECMB, the BAO at the time, and the distance ladder H0. This was, in retrospect, clearly somewhat contaminated by foregrounds. So we had the fabulous Planck 353 gigahertz map, which we're very pleased to have. And by cleaning the WMAP data, it reduced the optical depth somewhat here. And there's lots of published values of optical depth now with different data combinations and different analysis techniques. I'm only putting two of them up here to basically show that the value is, seems to be settling down, even though the uncertainties still aren't maybe as small as we want. But part of this is to share the news from the class observatory shown on the right here. Toby Marriage at Johns Hopkins is the PI of class, and just recently we did a cross power spectrum with Planck, and that's the Planck 100 and 143, and that's published by Lee et al. And you can see that number there also falls, somewhat in the neighborhood of what things seem to be settling out as. I expect if we can keep class going longer that we'll have a class-only measurement and a much stronger cross with Planck. So even though we're reminiscing, I'm also sharing some news. And so let me move on now after that very brief science summary to some lessons learned. I subscribe to a position actually taken by the US National Academy of Sciences that there should be, in terms of space missions, there should be a power spectrum of mission sizes, like one big, expensive $10 billion mission. But then as you go down in the price, there should be more opportunities for smaller size missions. You could see that I was involved in trying to generate some of that earlier on. So another lesson learned is that W had low, what I call transaction costs. I don't mean this just in terms of money, I just mean how to do business. And we had only one country to deal with, only one funding agency. Our budget was predetermined, and NASA kept its word and gave us the money when we needed it. And we had a small coordinated science team, so n-squared interactions was kept somewhat minimized, and that worked for what we were doing. I'm not saying that's a good recipe for everything, but that worked well for what we were doing. I started to appreciate during the WMAP times what I now call the golden rule of management, which is that lines of authority and lines of responsibility really should be coincident as much as possible. Telling one person they're in charge of something, and well, the other person has the authority for making decisions or spending money really doesn't work very well. Fortunately for us on WMAP, that mostly was worked out well. There were just a couple of occasions where needed to go to battle, but mostly that flowed very nicely. It may be obvious, but there's no substitute for experience. So we had a WMAP science team that had deep experience with the relevant hardware and experimental techniques, and this was really key. I didn't view WMAP as an instrument on a spacecraft, but rather the whole thing was a science craft. We had all kinds of requirements levied on the spacecraft components, and some of it was difficult for the engineers, and we actually had science team members step in and work with the engineers to try to work out what needed to be done, which brought this nice quote from one of the engineers that I remember. He said that I never knew that scientists could be so helpful. So when we originally selected team members and on through the mission, we were choosing people for their complementary talents and skills for what needed to be done. But one of the nice things about the small size is everyone on the team knew at all times what everybody else was doing, and people would report on their progress and what they're working on, and they would get helpful suggestions, critiques, whatever, from the others, and it kept it all very integrated and frankly pleasant. Computers, I remember Kobe started with like one ridiculously incapable computer as the requirement, and by the time it actually flew, from being proposed in '74 to launching in '89, as Chris described, they had a room full of computers that was possible over those years, all of which combined may not be more powerful than my cell phone, I'm not sure. But my basic lesson here, and this happened with WMAP too, is just don't worry about computers. The computers and the software are going to get much better than you can imagine. CMB foregrounds have always been a limitation for cosmic microwave background research. Multi-frequency observations are a necessity. DMR had 3 bands. WMAP had 5, Planck has 9, Lightbird I think has 15. What's happening is you're trying to make finer and finer measurements. You have to measure the foregrounds better and better. And now I'm going to go out on a limb, and I'm going to say that I don't believe any of the foreground models we have now are completely correct or detailed enough. I mean, the whole story of the foregrounds is learning stuff, getting new observations, fixing up what we thought we knew, and I don't think we're done with that. Obviously, we're getting to closer, finer measurements. Just to comment on the tensions, the cosmological tensions. You can tell, I can tell, as an experiment collects more data and data analysis improves, the tensions tend to either get bigger or smaller, any individual tension. And I showed you the Hubble tension, and over the years that's gone from being not statistically significant but noticeable to something that's got a lot of sigma. It's growing. I'm not saying what I think it's from, because I don't know whether, what kind of measurement or astrophysics or whatever, but there's something going on there. The S8 tension, for example, my view is that's just largely abated and gone away, so with new data. So it is, a technique to use if you have, increasing precision to data, whether things are getting better or worse. And I think that, yes, I was going to end on questions. I'm not going to answer these questions or discuss them. In fact, we have sessions that are going to address some of these. These are simply to say things that are on my mind that I would like to know more about or like to know solutions for. So let me just conclude by saying that cosmology, CMB in particular, has come a very, very long way in a very short time, and we still have a lot to learn. So I'll leave it at that. Thanks.
Thanks, Chuck. So we're going to defer most questions to the discussion session, where we'll also have questions from panel one. But if there's one quick, immediate question to Chuck, we can take it now. Okay, otherwise, let's move on. Let me invite Reno Mandolesi to the podium for... Here's Reno. Come over.
Thank you, Paolo. I need some water.
Where's the... okay.
Thank you. Thank you very much, Paolo. Hello, everybody. Let's start with
the laser and to move your slides.
I move it or you move it?
You move it.
Let me see. Okay. Let me start with some personal memories and the issues and gratifications. On this issue, let me congratulate with George and Dick for their recent Gruber Prize taken a few years ago, a few days ago. Sorry, you didn't know. Okay, going to memories. I think I can start with the early 70s when, for discussing my thesis, I was given the Pences Wilson original article. Can you hear? No, okay. Original article and discuss it with my thesis. Then later on, we, together with Bruce and with other people, we started some impossible experiments and learned how to build radiometers, but that was a dream. Then in the late 70s, 80s, we started measuring the spectrum of the CMB, and we did the best measurements before COVID virus. And then in 1992, I started thinking about cobras. So, talking about the Berkeley Italy Spectrum collaboration and with other college, the truth is that with Bruce, we talked to George to see if we could establish a collaboration. And so we did. And this was recalled by George at the Nobel Prize lecture. Joe Silk, of course, started everything in 1967 with some of you afterwards. This is the spectrum experiment at White Mountain at the beginning of the year 80s. We measured from 2.5 to 90 gigahertz this CMB temperature. And this is July, 4,000 meters above sea level. And this is the part of the the crew. And I know that Marco Berzanelli later on continued the measurements. He was too young at that time. Okay? The best measurements before COVID virus are there. One, two, three, four, 5, 90 gigahertz. Then I played also some bit with the cyanogen, and they measured also the cyanogen. So then was the start for beginning cobras and Saba, 1993. What was Planck, then called Planck, was a world-class science mission, very risky, because there was no hardware off the shelf ready. Data processing very complicated, as we see and we have seen later on. But at the end, hardware and software were done, successfully, as well successfully were the results, the objectives. Okay, there are many areas of lesson learned: management, development, operation, science, technical, operational, data processing, and documentation. Let me go one by one. Managing structure was too complex. With the ESA project team, instrument development teams, ESA led the industry, consortia led the industry. Very, very too complicated. PIPM meetings and science team, was that the right answer? I don't know. What about the day-to-day activities? That was not taken care of. Dedicated working groups certainly helped a lot, okay. That was something which we appreciated. Lack of continuity in program managing. We changed, Jan, if I remember, 3 program managers.
Reno, don't move around too much because you have to look at the camera. You are on YouTube.
Sorry. I don't want to look to the camera. Okay. It's true, 3. We changed the 3 project managers, 3. At least 3. I remember 3. Funding was problematic. No certainties of funding during the full mission. PIPM is a funding agency useful, but not enough. So there was some problem we didn't solve. Support for national health agencies controversial, not ideal. And in the while, there was also the affair of sport, an experiment which should have been flown on board of the International Space Station, and this was something competing with Planck, and that was a hard time to pass. And we did it, fortunately. Or I don't know if not. Management, okay, schedule, too many sleeps, longest flight lunch delay among ESA missions. I don't call it delay, okay, let's call it time lapse, time interval. Otherwise I have to question with Jan. Instrument organization based on academics, postdocs, together with these industrial professionals. That was something which has to be adjusted. I think what we should do is to train academic research personnel as lesson learned to talk the same language of the industry is engineer, evaluating, managing costs, risks, schedule changes. Consortia with under institute, each with different funding, manpower, schedule problem. Inflation of meetings, telecoms, bottleneck of 80 people, too many telephone calls, too many meetings. Communication information not ideal, could be improved. Documentation used a huge number of documents, all necessary. I don't know, probably yes, but I don't know. Lack of first authoring papers, this damaged, according to me, that's a personal view, the careers of young people. This is a matter of discussion, I guess. Technical challenges, thermal design. I know that Jan will talk about this. The passive cooling was 3 levels, cooling chain, 4K cooler non-redundant, solution cooler, technology of solution cooler not tested sufficiently in space, V-grooves not easily accepted by the industry. And there is a contract. I remember discussion with, I don't know, it was Alcatel, was the industry at that time, to convince them that the V-grooves should have worked much better than the thermal design of ESA. Optical design, I know that Jan will talk about the demanding telescope, control of stray light, measurements on ground. Instrument, high performance, sensitivity, stability, difficult test environment. These are the technical challenges. Planck was a risky mission, not only several single point failure. A risk assessment today of Planck would have not be allowed Planck to fly. the success of Planck is certainly attributed to technical excellence, to the people, to the people involved to development, but also some luck that helped. I remember that at some time at the end of the commissioning, the sorption cooler, the 4K cooler stopped working, and it was reanimated by switching off and on again. And since then it worked to the end. Long and complex commissioning, preliminary verification operations, contingency operations that took a long time. Data processing, systematic effects. I know that Jean-Louis will talk about systematic effect. Easy to find the first level of, but already going to the second level, third level, it's very difficult. And it means a lot of parallel stream works. A huge amount of computing effort and scientific organization and management was required. Difficult tasks that was not helped by the non-hierarchical community, scientific community. And this is a comparison of launch delays. Let's not call delay, let's not debate about adoption, selection. The blue bars are the ones showed by the Director General at the end of 2024. And as you can see, the red bar was the one I added by computing since the beginning, the time elapsed. And you see that whatever you can say, Planck is the longest. Let's not talk, sorry. Let's not talk about the fast missions because those are different matter. So what I wanted to say is that I begin, that's a personal view, I begin at my early 50s or late 40s like this, and I ended up. This is what I am now. Planck is a great success, and we hope that we can learn from it and build even better experiments in the future. I think this is, and thanks to the more than 100 scientific institutes and supporting agencies. And that's it. I was short.
Thanks, Reno. I see you didn't make any attempt to hide the dirty laundry behind the space mission. But, and still a chance for a quick question, if there's one. Otherwise, let me invite Jean-Louis Puget to the podium. Reno, come here. So the third PI in our session after Chuck for WMAP, Reno for LFI, Planck, HFI, Planck.
Thank you. So what I will talk about now is how we deal with systematic effects in the data processing. Okay, so the Planck legacy HFI maps were delivered in 2013, 15, 18, and what I will do is talk about the extension of that in a better knowledge of systematic effects. So, systematic effects have not been fully corrected, even in the 2015 release. the analog digital the ADC, analog digital converter, had non-linearities which were not which was a surprise. And the Boller-Butter time constant transfer function with up to very long time, 20 seconds. So the end-to-end simulation also, which François Boucher pushed us to do, and were the tool to know that we were on the right track. Okay, so the solar system dipole has been measured at all frequencies and up to the 545 gigahertz. And the condition that all frequencies sees the same dipole direction, not amplitude, but direction. And that leads to predict a large scale dust spectrum gradient. So if you do the map of 100 gigahertz over 87, which is full, which is dust, only dust, you see that the gradient in latitude is about the same for all 100, 207, 143, 217, 353, and 545 even. So these frequencies, the condition will lead to that, and you can see basically that the differential measurements confirm the accuracy of the HFI maps, adjusted monopoles. So the tool, the solar system dipole is a very powerful tool, and that's what led to this number and these direction of the dipole. And so WMAP error bar is here for the direction. LFI is here, and this part is the direction for all these frequencies and several F sky. And you can see not for 545, but all frequencies are really bunched in this direction. The amplitude also is very, very, very stable, and even the 545 is that. So in 2015, we were not satisfied. There was a lot of residuals. And you could see here the progress in IQU. If you do a back of an envelope calculation of the signal to noise we have on the HFI, the signal to noise is of order 10 to the 5, and the 100 gigahertz, 10 minus 6, between detectors, the RMS, 8 to 10 minus 6, so exactly there, and 217 to 10 minus 4, which was what was expected. The residual solar dipole per survey is basically noise for the 3 lower frequencies. And each survey is a 6 months the mission, it's in the mission. And what you see for 353 is this pattern between surveys. So this survey and this one is are described in the 2 opposite directions, and so that's basically the residual for a big type constant. If we look at global angles, global rotation of the focal plane, you find we do simulation, distribution of simulations, which and that's the value. Let me look more at that. Threshold 1, for example, had between detectors of 353 a dispersion significantly larger than the polar, and so the 2018 residual at these stripes, and so basically, if you plot for a frequency the systematics, so the noise is the red line. This is the ADC non-linearity, and all that is the other systematics that we brought well below the noise. So we are almost at the noise, and the noise of the bolometer. So the ADC and the converter analog digital is basically what dominates for all these three frequencies. For another illustration here is that this is the spectrum of the with the parameters of the found by Planck, and when you do the cross spectra or the power spectra, you see that cross 100, 143, 143, or 217 are here. If you do cross spectrum, you gain basically almost an order of magnitude for the noise, and so that's threshold 1 and threshold 2, where you can see very So, for the I conclude on the slide with the tau parameter, which was the most critical, for which the polarization is critical. And so we reduce the error bar for all fraction of sky used, or L min, or the synchrotron removal. And if you remove one of the L, you still find it doesn't move very much, and within the error bar, red. So last, I plot here the tau parameter, of cosmological parameter, and WMAP 13 here and in here, and Planck. And what you see is that it's stabilized, and the error bars has been reduced through better systematic removal. Okay, thank you.
So thanks, Jalou. Focus here is clearly on the huge effort to tame large angular scale systematics and squeeze science out of that. I wonder if there's an immediate reaction, or perhaps I hope to hear lots of questions at the end then. So let's move on. Jacques, if you want, you can come here as you wish. Next speaker is Jan Tauber, who was the ESA Planck project scientist and chair of the Planck science team, and also within the mission took responsibility for compiling the lessons learned from Planck. So that's precisely at the heart of this session.
Okay,
Go ahead.
thanks, Paolo, for that presentation. In fact, as you can see, is this the laser? I'm no longer at ESA, so I'm not sure if I have the right to be called Planck project scientist anymore.
Well, you were.
On the other hand, I'm still around, so if you're looking for somebody to take the blame, you know, and I'm still there. And by the way, that was one of the main jobs of the project scientist, to take the blame when something goes wrong. Okay, so Paolo asked me to make a quick introduction of the history of the mission, so this is the one slide. And people have already said first proposals came in '93. That's a long time ago. And we were officially selected in '96. And here I want to mention that WMAP was selected, I think it was 3 weeks before Planck, something like that, right? So we went to the selection meeting, the big selection meeting, thinking that we were dead in the water. And if we were not, I'm convinced it's for other reasons, you know? So one can, well, you can ask me about these stories over a beer, because I'm not sure I'm allowed to tell them in public, Anyway, it took a bit longer than for WMAP to get launched, which happened in 2009, and then we operated for 4 years, which was 4 times longer than planned, which was great. We really needed that. And then the data releases out to 2020. Here, by the way, is a picture of Planck after the first assessment study. Was a very different mission than the thing that we launched here. And not only because of the colors, I mean, the performance of the mission was much higher. So in fact, we did use some of the long time period to improve the mission quite considerably. Okay, so here's just a quick look at the payload of Planck in pictures, basically. So we had this Gregorian-style telescope, and it fed 2 instruments. One was based on bolometers, spider webs, but also polarization-sensitive bolometers. And these bolometers were cooled to 1/10 of a Kelvin by a complicated multi-stage cooler made up of a dilution cooler, 4K coolers, mechanical coolers, and absorption cooler. And of course a passive cooling stage, very complicated. And the other instrument based on low noise amplifiers, HEMT based, cooled to 20 Kelvin by the absorption cooler. Rather complicated instruments. At the time, they were state-of-the-art, but we have to remember this is quite old technology by now. Okay, so since this is a kind of lessons learned session, I have to point out that we did make an effort at the end of Planck to try to extract what were the things that we thought went well and what were the things that we thought did not go so well. And we wrote that up in this document that you can find on our webpage. The question that arose in my mind as I was preparing this is for who are these lessons learned actually? Who can profit from them, right? It's not clear that we have a successor space experiment for Planck. Maybe we will have, maybe not, I don't know. So in fact, the main recipient should be ground-based experiments for these lessons learned. On the other hand, you have to remember, again, we're talking about 30-year-old technology for the detectors. That kind of detector is not going to fly anymore. maybe much improved versions of those. Maybe more importantly, we have to remember the camera we flew had less than 100 detectors total. Right? Every detector on Planck had a name and a surname. They were treated like babies, each one of them. Right? Now you have instruments that have thousands or tens of thousands of detectors. And it requires a different kind of switch in your brain to process them and treat them. And so we have to keep that in mind. Then we have the telescope, which was a carbon fiber technology telescope. My lesson learned from that is very simple. Don't use CFRP technology for this kind of mission. Okay? It gave us so many problems. Okay? I'll talk a little bit about optics, but this is about modeling and about how you use the optics and so on. That we learned a lot about. But don't use that technology again for a cryogenic, large telescope in space. And then we have this complicated 4-stage cooling system. I think, to be honest, each one of the elements of that cooling system was a kind of prototype. They had never flown in space, if not the first time they were built, maybe the second, and so on. So they were really working models, if you like. And that was part of the risk assessment that Reno pointed out. Planck was a very risky mission, largely because of these coolers. They worked though, so that was great. On the other hand, are you going to use something like that again? I don't know. You know? And certainly every mission I have done a little bit of work after this, they use a much more complex system with redundancies and so on that makes the whole system much more reliable. So, okay, so you have to keep that in mind. You have to also keep in mind that space experiments have very, particularities, high risk aversion that comes with a lot of technical consequences for the instruments. I mean, we all know that we cannot fiddle with instruments in space, and so you have to design them that way. So when you're looking at a ground-based experiment, it's a completely different approach. Very long timelines. I mean, we're talking again about a 30-year experiment, essentially. That doesn't happen in the ground-based. You have these really complicated relations between, I would say, political elements, funding agencies, industry, science, and that also complicates these missions considerably. And the very large international scientific collaboration. It becomes more common in ground-based experiments also to have very large collaborations, but these are extra large, I think. And certainly, when we did Planck, it was very uncommon for an astronomy experiment to be done with such a large collaboration. So we were learning at the time how to do this. And these things have consequences on some of the other aspects that we addressed in this document. So, I mean, I think it's a good document, but you have to take what is written in it with some caution. So I did want to talk about optics a little bit. So again, we have the Planck offset telescope here, made of carbon fiber, and you see here some of the problems in this interferometric image of the secondary. It's not the primary, it's the secondary. The backing structure prints through into the front of the mirror, of the reflector, if you like. And that causes all these grating lobes and all this horrible stuff. It also makes a lot of difficulty testing on the ground. Okay. Now, one of the things that we did on Planck was we spent a lot of work, a lot of effort in modeling the optical response of the telescope. So we did a lot of these things, mostly with GRASP as a tool. And the other thing we did was we spent a lot of time trying to characterize the telescope on the ground. So there were lots of things that we wanted to do, but we could not do because of the difficulties involved here. But we did do a lot of RF testing in this big chamber. We did also infrared interferometry on the reflectors. We did things like videogrammetry and other things. So we did learn quite a bit about how to deal with the optics of such a system. So here's a few of the things which I thought would be worth mentioning. First of all, as we know, optics is one of the things that really determines the quality of the result for a CMB experiment. The requirements are extremely challenging, right? The performance you want is very challenging, and you also need to know things very well in flight. One of the problems we encounter is that you start out with an engineering problem, and you end up with a science analysis issue. And the language changes dramatically from one end to the other. And this is something we did not account for in the early days, and something that's worth remembering. You really have to be able to translate engineering speak to data processing speak to science analysis speak. Okay, you have to demonstrate performance, and for that you have to do modeling, first of all. And there again, we have a language problem, because, I mean, this payload was a kind of a mix between a radio antenna and a far infrared instrument, and everything in between. So you have different languages, and engineers that are used to different languages, radio, infrared, optical, you have to cope with that ability to translate from one language to another. Also between science and engineering, which is this problem here. Coordinate systems were, surprisingly, a very difficult problem. Everybody uses their own, and you always make mistakes, especially when polarization is involved. Translating coordinate systems is a pain. I can tell you, we found issues up to the very end, up to the very last data release. We found misunderstandings and problems in this very fundamental thing. This is something that really needs to be looked at. Now, in your modeling, you have to include all elements in the optical chain. It's not just the telescope, it's the feed horn, it's the detector at the back of the feed horn. And these are difficult to model. Okay? We never were able to model a full chain, never. I mean, with a detector in its cavity, or even, with filters and things like that. That's very difficult. Now, there are many tools that you can use. We use mostly GRASP, but we also use Code 5, an optical tool, ASA, which is an infrared tool, ZMAX, etc. They're all different. They all have different limitations. They all have different requirements, but the common thing is that you need experts to run them. Scientists, you don't pick this up in a weekend. Okay? So this requires engineering expertise, and it requires computing power. And here I would say, a little bit in contrast to what you say, don't worry, but the reason you don't need to worry is because you will always use as much as you can get, and it will never be enough. Certainly for the optics modeling, we never had enough. We never could model everything that we wanted to model. It was just too cumbersome, too long. So you have to extrapolate from what you can model to other things you haven't modeled. And that's a science per se. You have to learn how to do that. But principally, you have to decide how much can you reduce the modeling problem to. And then none of these tools really give you a way to assess the uncertainties in the modeling. That's a really big problem, I would say. We did manage to do some Monte Carlo with Code 5, but for the other tools, it was just guessing, essentially. Modeling. So then you do the ground measurements, and here the basic problem is clear. You cannot reproduce the flight situation in a test environment. Okay? This is cryogenic environment in which you operate an actual instrument. You can't do it. And so that means that you have to combine your modeling with the ground testing results and extrapolate a model which you think is telling you what you will find in flight. Basically, the ground measurements are just verifying the assumptions you have made in your modeling. Okay? And that's the frame of mind that one has to have. And then, of course, when you have done this combination, you are still not certain of the uncertainties at the end, in particular because you have operational constraints, operational aspects which come in, such as scanning and pointing, which also have effect on your beams. Okay, so I would synthesize my lessons learned there into these 2 bullets. First of all, you can only do a flight performance estimation on the ground, and it will be a combination of modeling and ground testing. And the problem is a system problem. So you have to treat this from day one with a single team that can cover all the aspects engineering to science. Okay? So that would be my recommendation. And in the end, I think it's inevitable that you have to assume you will have to measure the performance in flight. You know, that's an important driver for your operations and for your performance assessment. And yeah, maybe dedicated measurements will be necessary. So a little bit about operations now, switching topics. We planned for a very decentralized operation in Planck. I mean, the satellite was essentially operating autonomously. We had a 2-hour window every day to download the data and upload commands. We planned initially to perform 2 all-sky surveys, which was far too little, but this is what we thought we could get away with during selection. And from then on, you're stuck. You can't change your mind again. And the main goal for operations is to maintain instrument stability. Once you set those instruments, you don't want to touch them anymore. They have to remain stable. So we had this center that was doing satellite operations, 2 centers doing science operations for each of the instruments, and this other thing in the middle for various reasons. Important thing to realize is that operations don't start after launch. They start long before launch, okay? Every time you do a test on the ground at system, subsystem, subsystem level, it generates data that you may need later in flight, okay? So yes, operations start long before launch. And actually, when we started developing Planck, we were given a lesson learned that came from the ISO days, the Space Observatory days. And that was to do smooth transition between phases, and nobody knew what that meant, really. And I think after all these years, what I would say it means is that basically all of the ground testing teams should become the flight operations teams. And that ensures the knowledge goes through. And at the same time, all the tools or the procedures and the data that you generate during ground operations should also transition into flight. And that's important. I think we did relatively well there, but you know, there were a lot of things we could have improved. That was an important lesson learned that we got and that we transmit again. Reno mentioned that survey operations are not necessarily simple. And that's a fallacy that maybe doesn't exist outside ESA. It was certainly within ESA commonly known that, you know, if you have a survey mission as opposed to an observatory, 3-axis stabilized and so on, that the operations would be simple. But that's not necessarily the case. First of all, we had these decentralized teams doing the operations. That means a lot of interfaces. There are formal interfaces, files, basically, and informal interfaces, human interactions. And they're both really important, and they're both cumbersome. And then the performance verification in space can be very complex. For Planck, it was very complex, mainly because of the thermal situation. I mean, the whole satellite was reacting to thermal changes. And in particular, during the cool down, we had to be really have an intricate set of operations to do to keep the thing stable. Every time you touch something in the satellite, something else would be reacting to that. So this can be quite complex. And then we had contingency planning. So because we started out with the assumption that we could only do 2 full sky surveys, we realized early on that if we had any gap in the survey, it would have a very bad effect on the science. Okay? People did simple Fourier transforms, I remember, and came up with things that scared us. Okay? And because of that, you have to make sure that you can then fill up all those small gaps. And you have to do it within the 1 year that you have, right? The two full sky surveys. So we had to build a very complex machinery to actually allow us to react in time and fill up those little gaps. It would have been simpler if we had just planned for longer operations, but that was not what we did, unfortunately. Anyway, the lesson learned here is that survey operations are not necessarily simple operations. Okay, so here's again my summary is that ground testing is key preparation for flight operations. You spend as long as possible, especially on system level testing on the ground. And then you have to have this smooth transition. Formal interfaces are cumbersome, but they are important because as soon as you have a problem, you fall back on formal interfaces. If everything goes smooth, you can always talk to the operator, no problem. But when there is an issue, you have to have the formal interfaces. The human interface has to work well, of course, and you have to plan well in advance for operations in general. Yeah. Do I still have time?
Well, you are a little bit off.
Okay.
Try to be quick.
Yeah, I just had a couple more slides on some management aspects, which I thought would be important. Basically, here it is to say that, you know, in a project like Planck, we generate a lot of documents. And we all hate documents, right? But we all need them, unfortunately, right? They are the memory of the project. And we have to find a good balance between formal and informal reporting systems, documents versus other ways, wikis and so on, to ensure that no useful information is lost. And that's really difficult to find, that good balance. You need to manage documentation. You know, at the end of Herschel Planck, we had tens of thousands of documents that were, and I'm only talking about the, let's say, the ESA part of the system, not the science part of the system. And they all went into a system, and they disappeared instantly. You could not find them. You know, you put something there, and then finding it back, because it needs somebody that is recording metadata and that, you know, is doing things properly and not just, you know, just dropping something in there. That's just not enough. It really needs work, okay? And then data management is the thing I want to point out here is that useful data is generated long before operations begin. You know, as I said, all this testing data, and that must, in principle, remain available throughout the life of the mission, all the way to the end of the data analysis. So you really need a common archive. I think this Euclid really picked up this on this lesson learned, and I don't know how good a job they did, but at least they did do that. And this point about understanding the data, which in my mind is not the same as doing the science analysis. Understanding the data is having the confidence that you understand the origin of all the components of your data signal, okay? From the sky or not from the sky. And that is what needs to drive at least the first parts of the data processing. Science analysis is, of course, a part of that. You iterate, and the science analysis gives you information on understanding the data, but they're not the same. And then there's this thing about detailed documentation and so on, that you really have to spend time on documenting the data products. So, information and data exchange, storage and distribution must be actively managed from an early time, and this requires significant dedicated effort. I think it's something that as scientists we lose sight of often, and in our collaborations we give this very low priority. But it requires high priority, okay? It really is important. And as my last slide, Paolo, is I talked a bit about data and information management, but people management is the hardest problem of all. We have these large collaborations now, and they consist of a whole lot of people with different everything, basically, right? Expertises, timelines, obligations, needs, wishes, and expectations. And you do need some kind of formal hierarchy to make decisions, right? And in a project like this, there are constraints. I mean, there are contractual arrangements, there are financial obligations, and so a lot of these hierarchy is driven by that, okay? And that's something that you can't avoid, unfortunately. However, success in people management is critical to mission success. I wouldn't say that an unhappy team cannot produce good science, but I think a happy team will produce better science. So we should strive to keep people happy. And in particular, young scientists, and this is where I always feel rather guilty in Planck, because I have this feeling that we didn't do good enough a job for young scientists. I wanted to point out this document here, which was produced by this Astroparticle Physics European Consortium. They recently worked with a number of large collaborations, mostly particle physics. But also Planck participated in that. Jean-Loup and I were involved. And Reno too? I don't remember. And they tried to summarize their findings about recognizing people. So you might find this an interesting thing to look at if you want to. Anyway, I think the final message I wanted to do is that these management is often derided by our scientific collaborations, but it shouldn't be, because it is critical to success. Thank you.
So thanks, Jan. Lots of practical, pragmatic suggestions that dive into project management as well, how to manage a project. Let's move forward since we are a bit late. So next speaker is Hans Christian Eriksen, expert of analysis in Planck and other projects, and took a point in putting together data from different experiments and make them work better. So Hans Christian.
Thank you. Yeah, so I take my task as sort of trying to discuss how the lessons learned from Planck, which there were many of, and we discussed them already, were put in practice towards the end of Planck, and how they should be or could be put into practice in the future. And the title of this talk is The Importance of Global End-to-End Analysis, and that is something that grew out of the HFI analysis, the LFI analysis, S-roll, N-pipe. All of these essentially led to this. In short, you can sort of summarize it in everything is connected with everything. There's another aspect of that, and the subtitle I would say is also, seriously, we should all work together. This is hard enough that if you're trying to do it alone, it's even harder. It becomes simpler if you work together. And to set the stage, just a reminder of the brilliant maps that came out of these experiments, both from WMAP and from Planck. So here is two examples, the WMAP K-band in polarization Stokes-Q, and LFI 30 gears Stokes-Q as well. These are now the state of the art and tells us essentially what the polarized synchronous emission spectra look like on the full sky. Fantastic datasets, legacy that will last for a long time. But with this sensitivity also comes the level, the needed precision, of course. And once you have this data, the natural thing to do is take the difference between them. And we did that in Planck. And once you do that, you end up with something like this. After scaling for a factor to take out synchrotron, you should hope that this is white noise. Clearly it's not. It has large scale structures at the level of 5 microkelvin or something like that, which is huge compared to the signal from tau you're interested in. When we looked at this, we knew that quite early. This is a problem. Something happens here that Planck and WMAP, LFI and WMAP doesn't agree. And one annoying thing about this is that if you look at that and know a bit about Planck, you'll see that a lot of that is the Planck scanning strategy. So we know that it's not only from WMAP at least. We knew that a big chunk of this is coming from Planck. So we were struggling very hard to figure out where this is coming from and how we could solve it. One thing we did was try to change the foreground model, essentially. What we found was that if we changed the foreground model a little bit between 2 iterations in the gain estimator, we actually changed this map. So what we did in practice was estimate the gain using the CMB dipole, after subtracting a foreground model. Then you estimate frequency maps, you estimate component maps, and you refit the gain using that again. And that's what you're looking at here. This is the difference between those. And he has the same structures from Planck. This tells us that the gain and the foregrounds are very, very tightly coupled. And once we see that, that's when we started thinking, let's do this again. We saw something change, let's do it again. But we didn't have an integrated pipeline. So calibration was done in Trieste. So people in Trieste made calibration, sent that to Helsinki. They made maps, sent those to Oslo. We made component maps, and then we went back and back. And the whole loop there took a month or so, even more with summer vacation. So in the end, this is what was published. And what you see here is essentially a plot of gain variations as a function of those iterations. So the first iteration, that was after like 1 month of processing. The second is after 2 months of processing. After 3 months of processing. After 4 months of processing, Planck ends. Now we have to publish. But there's still drift in this thing here. So we know that whatever we did now, it doesn't seem to have settled down. So now we have to do the best we can with this. So we try to marginalize all the uncertainties, but this is essentially what we ended up with. So if we now take a step back, what actually happened here? Here is a satellite. It takes data. You try to clean those with the data selection and calibration. You make frequency maps. You do component separation. You make power spectrum estimation, and you do parameter estimation. Usually those operations are done with different teams, different codes, different languages, and it's slow. And the underlying challenge here now is that essentially there's a tight degeneracy between the calibration up here and the components that you try to estimate down here. Everything is coupled to everything. So then, of course, Planck was analyzed completely separately from WMAP. So now you have 2 analysis pipelines that try to do this. And at the end, you're trying to compare the results from those 2, and you end up with differences. At this point, it's difficult to do anything with it. So how can we then improve, and what is the problem here? First of all, there are different challenges. One is gain versus foregrounds, as I just mentioned. Another one is that each of the experiments have their own particular scanning strategy, blind spots, for instance. Planck is not fantastic at BB Eligus 2 because of the scanning strategy. WMAP has other blind spots. Bandpass and beam uncertainties, as Jan was talking about, measure things on the ground, but that's still not good enough. You have the uncertainties when you fly. Other degeneracies, and I think the overall word here is indeed degeneracies. Anything you can measure well, that's easy. You don't spend time on that, that's done. But really it's the degeneracies that is the problem. And when the degeneracies couple to unmodeled systematic effects, the whole system can just fly off. That's where your challenges are. So if you think about how can you do better, there are 2 things that sort of happen towards the end of Planck. One is close the loop and iterate. So we did 4 iterations in LFI, I mean this thing here, taking those maps, feeding back there, and go back. 4 is not a huge number. You're not guaranteed to converge. The other thing that can help is the more data you have, the easier this thing is. So putting both WMAP and Planck together and use one to break the degeneracies of the other, that's an obvious lesson learned. At the time, of course, we only had WMAP maps, or had access to the timelines, but it didn't work with them. So this is what we did. We tried to use some information from WMAP to break degeneracies in the foreground model that doesn't help Planck. Today, these lessons learned have been translated into what we call now the Cosmo Globe project, where the goal is to replace the separated individual code approach with an integrated framework where all this is done in once for all the different experiments at once, and thereby break the degeneracies, make people exploit the best in their data, the best possible way, in the most efficient way. So that's what we're talking about. Today, that's called Cosmo Globe. Isn't this extremely complicated, you ask? It's difficult to analyze 1 experiment. Is it easy to analyze 2? Well, my argument, it is, because the key is actually degeneracies. It's not coding. It's not writing the algorithm. It's solving the degeneracies. So one implementation of this is what we are proposing or working with is simple Bayesian statistics. So what we like to do is write down an explicit parametric model for the data, time-ordered data, that has some sky model here with beams and pointing and gains and asymmetric beam, orbital dipole, far side lobe, correlated noise, whatever. It doesn't really matter what it is, but you can write it down with a lot of parameters. Then you use Bayes' theorem, you write it down, the likelihood, priors, and you just sample it using standard Monte Carlo methods. So you can think about it, putting the whole pipeline into Kobaya. That's like the fundamental idea here, essentially, and sample everything at once. Does that work? It sounds amazingly ambitious. How can you imagine doing something like that? The first code that sort of followed directly from this LFI for loop iteration process is what is called beyond Planck. And that was essentially, the idea was indeed to continue with those iterations and not do it 4 times, but do it 4,000 times and see where we end up. So what we did then, you can see, recognize a lot of people here, was to take the LFI 30, 44, and 70 gigahertz time order data together with a few selected data sets from Planck and WMAP to control foregrounds, plug that into this machinery and see what we get. The products from that looks like this. So rather than getting 1 frequency map out, you get 4,000 frequency maps. And that's what you're seeing here, flickering through. And if you pay attention, you can see some stripes here. And what you're looking at there is actually gain fluctuations visualized. You see the gain fluctuations by eye here. And that gives you an idea of what uncertainties you have in the data on those. And everything else varies as well. Correlated noise, band passes, anything you think of varies here. Once you have that, you can actually go further and isolate the effect of each individual systematic effects in turn. And that's summarized for the 70 gigahertz channel here. So here is white noise, that's the gray line. Total sort of non-systematic, so variance that is not white noise. It consists of correlated noise, gain fluctuations, side lobes, bandpass leakages, 1 hertz spikes, and that's what's included for LFI. Then usually what is done in the low L covariance matrix is dominated by 1/f noise, the correlated noise. And that looks like this for the Planck LFI DPC covariance matrix. There's a slice through that, and you can see it is correlated along the scanning path. But when you do the whole thing at once and just map it out by Monte Carlo sampling, it actually turns into that. It's much, much richer. The structures are much stronger, and there are correlations that you didn't really sort of capture by this analytic calculation here. Another interesting thing for those interested in LFI, if you pay attention, you can see that at low L's, which is usually what we care most about, the dominant factor is in fact not correlated noise. The gain has a steeper slope here and overtakes it at very low L's, and it's actually about 3 times more important, the gain fluctuations, than the white noise. And that then plays a role when you get down to estimating tau or anything like that from this data. Is this just parameter fitting, or is it actually real stuff? So one of the parameters that we fitted was the 1/f noise slope, alpha. And what we got out when we just ran this was this curve here. This is the average of the centigrade detectors. And we were looking at that. Wow, that looks odd. Is that real, or are we just now in numerology and just fitting stuff? I think it was perhaps Marco Bersinelli who said, you know, that looks funny. Why don't you take a look at the thermometers from the focal plane and see if it correlates with any of those? And boom, that's what that looked like. So now you actually have an extremely tight correlation with the noise properties that actually varies as a function of something that is measured by a thermometer on the telescope. So yes, it's not just numerology, it's actually physics. And of course, when you then compare that with the traditional way, where we actually, in the early days, just let's assume that this is constant, or minus 1.2, clearly, I mean, the constant approximation here is not as good as you do it when you do it all parameter by parameter fitting. So it allows you to dig deeper into the systematics. And of course, that then translates into better control of the systematic errors and more realistic uncertainties. So that's something Jan brought up in his talk. You have to propagate uncertainties to the end in a stable way, something that is controllable. And if you only do like the standard stuff, you get the red stuff. But when you couple everything, and including the gain in particular, it's broader by about 30% and gives you more reliable uncertainties. So capturing all those uncertainties is a key lesson learned from Planck, I think. What about the actual results? Once you have all those samples, you can take the average of them, and that's what's shown here. This is the 30 gigahertz map. You can compare that with the legacy DPC map, and you can see they are similar, but they're also different. You take the difference between those, and you see those patterns that we actually discussed earlier. Very, very similar. to what was shown in the Planck analysis, Planck versus WMAP. If you then, so this is the actual map, the difference between WMAP and Planck legacy that was published. This is like in the literature for the legacy for each of them. If you replace LFI with beyond Planck, you get this. So you can see that whatever happened during that processing, beyond Planck is definitely closer to WMAP. So that's good at least. Okay, it's a good sign. But there's still residuals here that are still bigger than tau. And at this question, we ask ourselves, is this because we didn't do a good enough job on LFI? Or is it something still in WMAP? Or both? Could still be there. So that's the starting point, what is called now Cosmoglobe Data Release 1. And this is the first time, as far as I know, that 2 major experiments have been analyzed in the same code at the time-ordered data level. So we're not taking the LFI data in the previous one, but now starting from scratch in both of them. Still a little bit of other data. The team there is from 2021, so most of this happened during COVID. That was a very efficient way of getting people to work without, they didn't have anything else to do. And if you now go back to the comparison point again, this is the legacy comparison. This is if you only change, that's Q-band. Again, you can see that they are similar, but they are different. And this is the difference. This time, color scale is 5 microkelvin, so very, very lower. But still, I mean, it's a few microkelvin, still big. Here is the comparison again between WMAP and legacy LFI. You change out LFI, it goes to that. You do both LFI and WMAP at the same time, and it goes to that. Now, it finally looks like noise. And to the level that you can actually see spatial variations in the spectral index of synchrotron near the galactic plane. So this is now something that you can actually, for the first time, use data for both data sets at the same time. That's a good point. So with this in hand, you can sort of go back. What actually happened? Why did the 2 experiments disagree in the first place? And to us, I mean, it always boils down to the gain. Gain versus foregrounds is the big challenge here. So here's a cutout from Duncan Watts' paper. He was leading this analysis. And you can see that the 2 curves agree quite well. The WMAP seemed to fluctuate a little bit more. So on our side, we used the CMB dipole to estimate the calibration as we did in Planck, directly without any instrumental prior. So that's the difference. This is the corresponding one for LFI. Cosmoglobe Data Release 2 is the green one, while the official one is the red one. If you turn that into fractional uncertainties or fractional differences, you can see that the WMAP agrees with the Cosmoglobe agrees with WMAP to 0.3%. That's pretty good. That's a pretty good job. On the LFI, it's a bit bigger, 1.2%. So that's a 1-to-4 ratio. So a favorite pastime of many cosmologists is the so-called blame game. So if you go to that, in this original map, now we can sort of say that about 20% of that came from WMAP and 80% from LFI. That's in 2020 hindsight, when you have sort of a model that agrees with everything. Again, is it surprising that they agree? I mean, you analyze them jointly. Shouldn't they agree by force, essentially? To address that, here's an illustration of the WMAP W band. And of course, that is known to have very strong poorly measured mode residuals. And that's why it was not used for the cosmology part of that, essentially. But here's compared with the Planck N-pipe results at 100 gigahertz, and they are very similar. And if you take the difference, the galaxy disappears, and you end up with something that looks like the WMAP poorly measured modes. We didn't actually look at this until the end because we were so focused on K-band. When we actually looked at it, it came out like that. So here, HFI was never used in the analysis at all. I mean, this was never used for the analysis, only, So it shows that actually you are fitting something that makes it closer to HFI, and I think we agree that HFI is probably a better estimate of the real sky here. So that shows the power of sort of the global end-to-end analysis, where you feed information from the gain to the foregrounds and back again. And of course, with this in hand, you wonder, what are the implications for other things? Right now, what's ongoing is what we call Cosmoglobe Data Release 2, where it's extending to the Derby and infrared sky. So taking the lesson learned from WMAP and Planck and apply it to other fields of science. Chris was alluding to this analysis earlier. In this case, again, take the Derby TODs that have been around for 30 years now and plug it into the same machinery, couple it with Planck HFI maps, WISE and Gaia for point sources, and FIROS for absolute calibration, run the machinery, see what you get. So here is the legacy Derby map that has been around since 30 years or more now, at 4.9 microns. I mean, this is an important channel for things like possible optical depth, COB, and PAH information coupling with 3.3 microns channel. This is supposed to be ZODI subtracted. It's important. This is after ZODI subtraction. Unfortunately, the Derby team didn't manage to get that far down. I mean, it is removing something like 98% of it, but still the last 2% are strong. When you do it in this global analysis, it looks like this now. So you can see how much better you dig down into the ZODI floor by using information from the other experiment. These are stars, this is diffuse foregrounds, and you couple information from different sources in an integrated framework. You dig deeper. The same thing for 12 micron, long-standing channel. This is the official map. That's the new Cosmos DR2 map that's being released right now. So you can see that now you can set much stronger constraints on the CIB monopole, for instance. That is the target of this thing here. Right now, there is a movie that sort of shows the sky from about 1 gigahertz to 1 micron that covers a big chunk of the electromagnetic spectrum in one integrated framework. And with this in hand, it's then much easier to add in new experiments and get synergies out of that. For instance, spherics is something we're excited to sort of try to put in and see if we can get synergies between spherics and the other experiments. So, what is happening right now? This is a list of the experiments that are currently being analyzed in the same Cosmos framework. SPIDER, FIRAS, Akari, Simon's Observatory, Simon's special case, HFI, IRIS, Lightwood, and KaiPass. And those are maps that are produced with the same code running now right now. Nothing of this is publication ready. You see artifacts, but it is running in the same structure, and students and postdocs are pushing on this, trying to get out their own results. ESO is in progress, and we hope to start working on that towards the end of the year or something like that. If you then look forward, I mean, the key lesson learned here is that it's much easier to be working together than separately. I mean, one person's problem is another one's solution. So, I mean, we have to break each other's degeneracies. And right now, there are a few major applications in progress. Ingunn is proposing a synergy grant and various major applications to Research Council of Norway. And if you're interested in joining, you should contact her now, because these will include a large fraction of the community. If you have an experiment that you think should be included here, you can benefit or contribute. I mean, this is the natural way to do it. And now is the time, before the summer, it's going to be written the application. So contact Ingunn if you're interested. Yeah, thank you for all the funding. Again, work together, that's the story.
So, I promised I would extract questions from the audience, so it's your turn to provide them. Francois.
What do you do when you're
Wait.
your own income model?
What do you do when?
Well, you say, let's just write the model and with all parameters, and we determine the parameters by breaking the degeneracies. What if you didn't include ADC nonlinearity?
Yeah.
So you'll get the solution. Well, let me just comment a little bit. You'll get a solution, obviously. It's going to be wrong.
Yep.
So at some point, you need also people that will do some other analysis than this, which are, so to me, this sounds like cherry on the cake. You need to have already the basis that has been written for you, and I don't see this as a community effort. This things of doing the thing, I mean, at the lower level, it's a small group of people that know what they are doing.
Okay,
so
let me take a
how do you take this?
I think that was for me. So let's take a practical example. Towards the end of Planck, we were looking at residual maps in this analysis. That is data minus model, as it comes out here. And we were seeing large-scale structures coupling with the galactic plane, and we're suddenly thinking, you know, that looks very much like polarization angle errors. We were then talking with Matteo Testram, Ray Keskitalo, and saying, could you please try fitting polarization angles and see if that helps? They did it, and then boom, yes, it solved it. So, I mean, to us, the big thing are the residual maps. You take the data as you produce them, minus the model, see what's there, and if that is white noise, yes, then it's great. But usually it isn't, and we're far away from that. I mean, and that gives it a handle on what to do. And this is true for anything, like polarization angle, that's a case that you know about. Bolometer transfer function, you see the residual spreading out from the galactic plane. All of those things pop up in the residual maps. And that's why it's important to always keep it in the lowest possible format you can, maps or in time domain, not just power spectra, because if you're looking at just power spectra, then you're blind, it looks something like that. That won't work. But the visual representation is something that allows your human brain to identify that looks like that systematic effects. And that's really where a massive power of this comes from. And having more experiments that shows you, you bring one experiment in, suddenly it all blows up, well, then you have something to work on that experiment. If you have a consensus of 5 experiments and then one is outstanding, then you know it's probably come from that one.
Hold on. Just another one, Francois. Yeah, just a comment. If you are saying that null maps are useful to identify systematics, I think that all the people that have been involved in doing this will agree.
Yep. It's obvious.
I mean, we're just saying when is a big machinery needed to actually proceed. That's
more question or discussion. So we have 3. Who went first?
So we didn't have a Q&A in the previous section. Are we allowed to ask questions to the speaker of the previous section? Yes. Okay, then my question is to Professor Rashid Sunyayev. That you, in one of your slides, you show this interesting distortion in different epochs of the universe. One is mu, and there's I, and there's Y distortion. I heard about mu distortion and Y distortion, but I have never heard about I distortion. There's this little I distortion, I type or something. Can you explain it?
I is intermediate between two. And I hadn't time to show. And there are things in between. And you can find at what redshift exactly energy release occurred if in this intermediate region. And this is absolutely great if you have enough channels. And energy release occurs, for example, at redshift 10 in power 5 or 10 power 4. You can exactly find what is at what time energy was released and so on, because intermediate spectrum intermediate type of spectrum permits to find when it was created. Excuse me.
More questions? Absolutely, also to panel 1.
Yeah, hi. I have a question on the optical depth, and it was very nice to see the evolution of the optical depth has been shown, and also to see there are new measurements that are complementing Planck. Still, while you said clearly that the value of tau E has almost stabilized in the last years, yet the errors are not are still relatively large, and I'm asking this from the point of view of reionization that I will touch a little bit tomorrow. There are many reionization models that still pass through the errors, and so it would be great to know what are the prospects for the future to decrease those errors.
That is a wide question. Maybe you want to start, Jean-Loup?
Well, I think what I have shown is what I don't think with the Planck data we can go a step more.
I showed a cross power spectrum between the class experiment and Planck. If we can keep the funding going, which is difficult in these current times, I believe, my personal opinion is that class will make a cosmic variance limited measurement. From the ground. Yeah. Oh, sorry, I didn't hear that.
And what about foreground?
We have multiple frequencies on class, and we also have other sources too. So I don't promise, but I believe that would happen if we can keep running.
There's also live programming for rats.
So if we look forward to a future CMB satellite mission, perhaps it would be somewhat simpler than Planck, one hopes, but it's going to be a lot more sensitive, 30, 100 times more sensitive. And so it seems to me the central challenge is systematics control and integrating that into the design. So I'm curious, Chuck and Jan, based on your experience, if you would have a single recommendation, like structurally, how you would build or organize the CMB experiment with that challenge in mind.
I would echo what Chuck said before, a small team, okay? And as clean an experiment as you can make it, where you can measure all the quantities that you need in flight and you don't rely on ground measurement. That's all I could say.
A small team, a short time. So the other...
Speak closer, Reno, to the mic.
A small team, a short time. That's certainly something that one should look at. The other point is, a question to Jan. If you could have used silicon carbide technology, would you have built the Planck telescope in it?
Well, I mean, it would have been a better telescope, and we would have measured it better on the ground, yes.
Too large for probably, but...
No, I mean, I think it was too heavy for us. The reason we selected the CFRP was the mass, and because, well, there were some other issues about the heritage of the... We had developed, that technology had been developed for Herschel, and was found wanting for Herschel, and then there was a will to use it somewhere. And so...
Next mission.
Do you want to follow up on Jamie's question?
Yeah, I really think the place to start is to really focus on what science needs to happen and to make sure that that's what you're doing and not, I've been in groups with many scientists and it usually goes like, and it would be nice if it did this, and it would be nice if it did this, and that's where you run into trouble. I think you start by saying exactly what science you need to do and what do you need to do to get that done, and keep the other stuff out of it.
There's one question here. First, Julian, and then George.
It's really more of a comment on the discussion about computing power, but bringing in the parallel history of computing, and Jan's running into the limits of computing, I think, really ties to the end of clock speed as a way of increasing serial processing power or very limited parallel processing power. And once you start melting your chips, you really can't clock them any faster. And so that really hit for things like grasp that is notoriously unparalleled. Obviously, Moore's law was then developed by going to massive parallelism. And so that's where exactly, as Chuck noted, by the time you've launched and run your mission, Moore's law will have thrown you an exponential growth in power. Of course, with the end of Moore's law, that's no longer the case. So I think future experiments are going to be hit with the double whammy of a horrendous shortage of both serial and parallel computing.
Who wants to take it? Chuck again.
Yeah, I just wanted to make maybe a clarification of what part of what I meant was I worked on 2 space missions on COBE, and the original computer requirement documented for COBE was ridiculously inadequate. WMAP, we did better in documenting what we need, but this is partially a lack of vision of what you're in today's mindset of what statistics you want to calculate and things like that, and you're going to want different things in the future, and software is going to make it so you can do different things. I mean, there are things that are done now routinely that we couldn't have really done. So my concern is that if you're saying in advance what computer power that you need, you will probably underestimate and probably by a lot.
Yeah, it also surprised me a bit that no speaker emphasized the need for simulations, which was not anticipated in the very first moments, and then it came out as a necessity.
Just a word on GRASP in particular. I'm sure that tools like GRASP will improve dramatically in speed, and have improved probably since the time we were using it. But at the same time, now you're talking about tens of thousands of detectors. So, so these two things end up balancing each other, and I think you will hit some limits. As I said also, you have to find a switch and see, how you approach 10,000 detectors instead of a few, in terms of things like the optics.
500,000
Okay, then we had George.
Yeah. So I guess this is directed to Chuck, because I completely agree that if you are asking a question like how tight a limit can you set on the tensor scalar ratio in the face of foregrounds? We don't know the foregrounds well enough to answer that question, and so you'd better go and measure them, right? So, if you have a wide frequency coverage, then you pay a penalty in the complexity of the data. And there's an alternative strategy that if I didn't know very much about the foregrounds, I could work where I think the foregrounds are simplest, so I could go to high frequencies and have relatively narrow bands and kill the foregrounds with signal to noise. So that's but it's not an alternative, it's not a strategy that any experiment that I know of has adopted.
Yeah, so I agree with you. You can try to implement clever strategies, but what if there's a low-level foreground we don't know anything about, but it's stronger than you need for the V modes? Or in Hans Eriksson's work, this is similar to the earlier question. You're combining information through, I think, a sky model in your equation, right? And suppose that there's components that are relatively small, but not in that sky model. You will reach a solution, but it won't necessarily be exactly the right one. I assume you would agree with that.
Yeah. So you always have to couple it. Yeah. So you always have to couple it with rigorous goodness of fit test, residual maps, cutting the data in different ways and see if it's consistent. I think the idea of going for a minimal solution with narrow bands and stuff like that, to me that is dangerous, because there is an inherent complexity to the sky, and trying to sort of tune your experiment to hit a soft spot, that's dangerous. My gut feeling is that you'll end up with something that you can't distinguish from a real detection. And I think we don't have any choice but going for the big solution and actually dig down until we see it. And then have multiple tests to see that it actually makes sense compared to a physical model, different experiments or complementary experiments to the reionization peak and the recombination peak, perhaps one that does everything at once. But yeah, you need multiple tests and just hoping that you are lucky and the sky is kind to you and you can see through somehow at selected frequencies of sky spots. That's a bold approach, I think.
More questions while the mummies wait for us. They've waited a long time.
This is not a question, but an observation. We've heard a lot today from observers, people who've designed and built equipment. What has been less recognized, I think, except by Hans Christian and Rashid, is the tremendous role played by theorists in telling us how to interpret the data and how to wring information out of the power spectrum and so on. I think we're not quite yet at the quantum limit, which I define as the number of papers equal the number of photons received. But it's close. But it's also very, very valuable.
Okay, thanks, Bruce. Time for maybe another one. Yeah, Eiichiro.
Yeah, so I very much like the idea that we want to do something focused. So we come up with scientific questions we want to focus, form a team that's very focused, smaller and simpler, and borrowing the word from David Wilkinson, I don't want to do everything, but I want to do something, do it sooner. What I learned over the last decade or so is that our funding agencies don't like that approach. And I think this competition is getting very, very severe. And we see these wonderful astronomical missions doing planets, great observatories that do multiple things. And it looks as if that was the most important thing. It's most like a beauty contest. Whoever wins is the one with the largest supporters. So when we went into ESA or NASA or JAXA and say, we wanted to measure one thing, they just don't like it and just turn us down. Even if we wanted to have simpler team, they demanded that we have to grow like a Christmas tree. And we failed again. So I just don't know what to do with it. I mean, in principle, my heart is with you. I just want to do like that, but somehow we can't do it. Spectral distortion, it's no-brainer. But in the end, what they are told is you can't just measure Y, you can't just measure mu, do something else. Then the team grows, right? So do we have any insights into how to deal with this issue? We're somewhat stuck.
So very interesting question.
I mean, you've put your finger on the really difficult thing. I feel your pain. I've seen this happen. For example, we now have the Roman telescope, which started as JDEM, a joint dark energy mission. It was a dark energy focused mission, a physics mission. But it turns out there's a lot more astronomers that want general purpose telescope time. So it morphed over the years to be just what you described, bigger, broader, and all of that. That's the natural force that pushes things. I'm a realist. You have to work in the real world with real constraints, even if they're not ideal. But I do think that having the smaller, cheaper missions gives you a chance at doing those things. That has to be coupled with very strong science argument that everybody understands and feels like this really is something that should be done, such as happened with like WMAP. There was a strong consensus that something like that should be done. So I think the scalar to tensor to scalar ratio is difficult because you don't know whether you're going to set an upper limit or detect something, and that's a tough sell inherently. So yeah, but I would say it really does help if there's an idea that the community really gets behind, even if not everybody's on the team. If everyone says, yes, this is important, this should happen.
Okay, we had, Eiichiro, you wanted to reply. Then Charles, and then Joe.
I didn't know that you said that initially the community was very doubtful about the WMAP's capability to determine cosmological parameters, right? I didn't know that. So maybe what you're saying is better PR should be a part of.
Yeah, I think it starts with colleagues internationally and talking to people about what they really are excited about.
So we have to convince the community also.
If there is no consensus in an international community that something is all that exciting, it's going to be hard to to push it forward.
Yeah, got it.
Okay, then Charles.
I'm going to suggest that we ask Jamie Bach to describe how Spherex dealt with precisely the issue that Eiichiro raised. They did it brilliantly.
Right. So, Jamie, do you want to give advice?
Well, I think there's an issue of money involved. Like for the Medium Explorer, you can propose to do one thing. It's a competition. but you can do that. I mean, I would have done it if there was just really one thing to do with spherics. So that was a happy coincidence. NASA's doing an experiment now with probe missions, which are 1 billion, which are also competed. I don't know what's going to happen in the coming years because it's very turbulent right now, but that might be an opportunity. With these facility missions, which are generally astronomy missions, it's very hard because of the desire to do everything.
Okay. Then I had Charles.
Let me give the answer I thought Jamie was going to give, which was Spherics was designed to do 3 things. But well before it was open to the community, what would you do with the Spherics data? There were 2 workshops that Spherics organized that got tremendous response from the community, such a tremendous response that the community organized a 3rd workshop for what they would do with the Spherics data. So, data designed to do 3 things really well, do a whole lot of things. That, I think, is the best way to make it work.
Okay, let's move quickly since we have the visit. Joe and then Nabila, right?
So just to comment on doing more than just searching for one number, the obvious example is spectral distortions. If you do a good enough, big enough experiment, you can not just get YMU, but you can get the recombination lines, even the helium recombination lines. And that would be the most amazing science return. It's guaranteed science return, but you do need a very big experiment.
We're going to have a full panel on that. Right. Nabila. And then you, and then we close.
Thanks a lot. It's to echo indeed this discussion about spectral distortions. I think that some science cannot be done with a couple of tens or hundreds of million euros or dollars, and some objectives, I mean, they need a lot of money, and that's it. It's quantized, let's say, and we have to do the best of it. That's for sure. We definitely have to avoid the Christmas tree syndrome. But I think that it's not obvious to target some type of science. I mean, there are steps, there are roadmaps. It's like if I take something which is completely different from what we're discussing right now, it's the Martian program of the search of Mars. You start with an orbiter, then you do some cartography, and then you put rovers, and then you try to get samples. And we are at a step in cosmology where we have reached the level of precision that is needed, which cannot be done without big missions. And this is something that we have to indeed make our agencies understand, and our scientists also understand as well, because we can't do everything with the same mission.
That was more of a comment than a question, I believe, but reactions are welcome. One last.
My question is simple to Jamie and to Lawrence. Is Sphere X okay under Trump?
Okay, that's what I thought. Okay, so let me get back for a very last question I'm gonna take as chair here to the panel, lessons learned. One radical difference between Planck analysis and WMAP analysis, teams with very different size, but WMAP analysis was much more compact in the pipeline. So one map maker, one component separation solution, one likelihood. Planck was more widespread. We published 4 component separation solution, a couple of likelihoods. That was called as an added value. But my question is to whoever wants to take it, was it really worth it or not? He can't stand unanswered.
Let me just say that I think it's important to take into historical context that when WMAP was doing this, we were literally figuring out for the first time how to do some of these analyses, how do you analyze the polarization? We did use more than one foreground analysis technique, but mostly we were in a hurry and trying to understand it. So, you know, Planck was in a different period of time and had all that work already done. So it was maybe natural to do the different kinds of analyses and to be more complete. So, but I'm not going to attempt to answer the stopping point question.
But yeah, so I mean, these have been long...
Speak closer to the mic.
These, of course, have been long-standing discussions, and my personal feeling and opinion is that having multiple pipelines, multiple results is a good thing. It shows stability with respect to algorithmic choices. If you only have one, I mean, the community will ask, so what happens if you do that or do that? And it's difficult to answer that. So yes, there's an overhead, but there are also advantages. I think something that is worth having in mind, of course that's more true here in Europe than with the NASA-oriented approach, is that for us, something important is training PhD students and postdocs and allowing them to sort of explore things on their own and having a rich field. That is good for the training aspect. And so yeah, I mean, a single pipeline is easier in a small group than in a big group. If you have a big group with one pipeline of 400 people, most people are just going to sit and watch. So yeah.
Okay, if there are no more reactions, let's close the session here for today. For those who have registered for the visit to the Egyptian Museum, the meeting point is at the entrance of the museum, ground floor, and the others are free to go, and we'll reconvene tomorrow morning as planned. Thanks. Let's thank the speaker again.